Hi, I'm Sudhir, and today I will present a type of supervised regression called support vector regression (SVR). This is the basic outline of the presentation, starting with the introduction of supervised regression, and then we will know about support vector regression, its mathematical logic, and how it works. Then advantages of SVR. How good is it compared to other supervised regressions? We will see applications of SVR, where can we use it and so on, and then we will conclude. Introduction. Supervised regression is a type of machine learning algorithm that is used for predicting continuous numerical values. In supervised regression, the algorithm is trained on a labeled dataset where the input features and their corresponding output values are known. The algorithm learns the relationship between the input features and the output values in the training data and uses this knowledge to make predictions on new, unseen data. Support vector regression is a type of supervised regression that uses support vector machines to find the best possible line or curve that fits the training data and can be used to make predictions on new data. Support vector regression is particularly useful when the relationship between the input features and the output values is nonlinear or complex. Support vector regression. Support vector regression, SVR, is a regression algorithm that helps to find the best line or curve to fit data points in a regression task. It achieves this by separating the data into two classes using a hyperplane and minimizing the distance between the hyperplane and the closest data points. To do this, SVR maps the input data into a higher dimensional space using a kernel function, which makes it easier to separate the data points. Then, it finds the best hyperplane that fits the data by minimizing the error between the predicted and actual output values while considering a regularization constraint. In simple terms, SVR finds the best line or curve to fit the data points by separating them into two classes and adjusting the line or curve to minimize the error between the predicted and actual output values. Mathematical foundation. The mathematical foundation of SVR is based on convex optimization and the use of kernel functions to handle nonlinear relationships between the input and output variables. This allows SVR to find a hyperplane that best fits the training data and can accurately predict the output values for new, unseen data. The goal of SVR is to find a hyperplane that best fits the training data and can be used to predict the output values for new, unseen data. The hyperplane is defined as a linear combination of the input features and is represented by below equation. Y is equal to WTX plus B, where Y is the predicted output value, X is the input feature vector, W is the weight vector, and B is the bias term. Advantages. Robustness to outliers. SVR is less affected by outliers than other regression techniques because it only considers a small number of training points that are closest to the decision boundary. Generalization. SVR can generalize well to new data, even with a small number of training examples. Nonlinear relationships. SVR can handle nonlinear relationships between the input and output variables by using different types of kernel functions. Overall, the robustness, flexibility, and ability to handle nonlinear relationships make SVR a powerful regression technique for a wide range of applications. Applications. SVR can be used for predicting weather forecast. SVR can be used for weather forecasting tasks by learning the relationship between weather variables such as temperature, humidity, air pressure, wind speed, and wind direction, and their corresponding output values such as precipitation, cloud cover, and temperature. Predicting disease outcomes. SVR can be used to predict disease outcomes by learning the relationship between different patient characteristics, such as age, gender, medical history, and lab results, and the outcomes of a particular disease, such as disease progression, survival, or response to treatment. The SVR algorithm is then trained on this data to learn the underlying patterns and relationships between the input features and the disease outcomes. Once the model is trained, it can be used to make predictions on new patient data. In the same way it is used to predict pollution levels, modeling climate change, identifying risk factors, predicting customer behavior, forecasting sales. SVR can be applied in the planning field in different ways. Land use change detection to predict future land use changes based on historical data and trends. Traffic flow prediction can be used to model traffic flow patterns based on historical data, weather conditions, and other relevant factors. Real estate market analysis. It can be used to model real estate prices based on various factors such as location, size, age, and amenities. Environmental monitoring, SVR, can also be used to model and predict environmental factors such as air and water quality, noise pollution, and climate change impacts. Conclusion: Support vector regression, SVR, is a powerful type of supervised regression. It is a flexible and effective method for solving regression problems in a wide range of applications, from finance and economics to engineering and science. By fine-tuning its parameters and selecting appropriate kernel functions, SVR can achieve high accuracy and good generalization performance, making it a popular choice for many practitioners and researchers. Please don't like, share, or subscribe. Thank you.